In this video, we're going to apply the fundamental theorem of calculus to find the area bounded by the x-axis. So this axis here, the line x equals 2. Let's do that to here. And the graph y equals x squared. So y equals x squared, that's 1, and that's 4. We would have this parabola here, starting flat. There we go. So y equals x squared, x equals 2, and the x-axis gives us this region inside, and that region area is equal to the integral from 0 to 2 of x squared dx. All right, that is what we called earlier our little f of x, and we need a capital F of x, which is equal to an antiderivative of, in this case here, x squared. Well, we've actually been given that as a little hint in our setup here. If we have our little f of x is x squared, and we want to do the antiderivative, well, we're going to get 1/3 of x cubed. Because if I differentiate 1/3 of x cubed, I get back to x squared. So we have the antiderivative this way and the derivative this way. So 1/3 of x cubed is what we're looking for to apply our fundamental theorem of calculus. So what does the fundamental theorem of calculus say? It says I can evaluate this complicated beast, the area under this curved graph, something that's not circles, not rectangles, not anything else. I can evaluate that by looking at the x squared and saying, plug in the upper bound 2 here into my antiderivative, and then subtract what happens when we plug in our lower limit into the antiderivative. And our antiderivative here is just 1/3 of x cubed. So we're going to take 1/3 of 2 cubed minus 1/3 of plugging 0 into here, 0 cubed. So the important step here is the subbing in. Well, that's pretty easy. The fundamental challenge is going from this x squared to this antiderivative formula, 1/3 of x cubed. We're going to spend a lot of time on that, but it leads to a calculation here of 8/3 minus 0, or just 8/3 square units. And that is a huge milestone. This area is exactly 8/3 square units in size, in area, and that's something we could not have done with rectangles, approximations, circles, any other known area calculations that we've had up till now. This is a gateway to finding the area under any curved function in principle in a strategic and systematic way. So, awesome. The fundamental theorem of calculus applied in its full glory for the first time. Let's explore that a little bit, because there are some edges around here that are worth investigating. We use the fact that this capital F of x function, the antiderivative, was 1/3 x cubed. The question is there anything else that we could differentiate and get x squared? What could we put in here and still get x squared back? Well, you can try some things. You could try x to the 4. Well, no, x to the 4 is not going to give us x squared. Is there anything else? Other x cubes? Well, if I just have x cubed, I'm going to get a 3 out front. I really need that 1/3. There's no question that somehow 1/3 x cubed is going to be our building block if our goal is to get x squared after we differentiate. But then we think, well, what if I added 1 to that? That would still give me x squared after I differentiate, because the derivative of something added on the end would just be adding 0. Does that change our rules here? Because I could use this function instead and call that capital F of x. Is that okay, or does that break things? Well, let's do the same process. We're going to call this f of 2 minus f of 0. We're just going to use this new function and see what that gives us. So we're going to plug in 1/3 of 2 cubed plus 1. And then we're going to subtract 1/3 of 0 cubed plus 1. So we're going to get our 8/3 again, plus 1. But we're also going to have a oh, phew, we get the same answer back. Let's take a step back in the slides, using the fundamental theorem of calculus again, with a variation on our function, but one that still satisfies the requirement. This f of x, when I differentiate it, gives me the x squared I'm integrating, and I still get the same answer for our area under the curve. Because it turns out that plus 1 is going to appear in this first term, but then I'm always going to subtract it in the second term, and it's always going to end up canceling, which is exactly what we want. We want to keep this value, the area under the graph, the same. So did that value change? No. Phew. Why or why not? Because that plus 1 gets canceled or cancels with the f of b minus f of a difference. So the plus 1 in our function ends up being added and subtracted. Well, if that's the case, then if we go back to our x squared scenario, if we wanted to find a function that we differentiate to get x squared, I could add 1 to it, I could add 2 to it. In fact, we could add any constant at all to that 1/3 x cubed, and it wouldn't change the derivative. If we do that calculation, you can see it here. 1/3 x cubed plus c is always going to differentiate to x squared. And so we're going to see this plus c thing in this portion of the course a lot, because it's something that we could always include with an antiderivative and still satisfy. If I differentiate 1/3 x cubed plus any constant number, I will still get back to x squared. We'll explore this theme more in the videos to come.